Okay. So the barrel flow heat exchanger, our double pipe heat exchanger, when we have two concentric tubes. So the double pipe heat exchanger is basically two concentric tubes. We have they are sharing the same center line, where the cold stream is flowing in the inner pipe, while at the outer pipe the hot stream is flowing. So basically, double pipe heat exchanger is consisted of two concentric tubes. For the parallel flow, the cold stream is flowing in the same direction of the hot stream, and if we draw the temperature distance diagram, Tx diagram, so the cold stream is going to reduce its temperature from T hot in to T hot out at the end of the pipe length, and is going to be in this direction. And for the cold stream, is going to increase its temperature this way. So from T cold in to T cold out. All right. So this is for the parallel flow. For the counterflow is the second category of the double pipe heat exchanger. B. So it's counter flow heat exchanger. So for the counterflow heat exchanger, if we draw the same concentric tubes, so the cold stream is flowing in this direction, so the hot stream is going to be in the opposite direction. And the Tx diagram, sorry, so the Tx diagram, the temperature distance diagram, is going to be something like that. The hot stream is going to be the same, going this way from T hot in, T hot out, and the cold stream is going to be that way. T cold in, and it is T cold out. All right. So from the double pipe heat exchanger, we can, as I told you before, that there is something called log mean temperature difference. So the log mean temperature difference is going to be found only in the double pipe heat exchanger, right? So we call it delta T LM. So this is basically delta T1 minus delta T2 over ln delta T1 over delta T2, right? So delta T1 is basically this one. This is delta T1 for the counterflow heat exchanger, and this is delta T2 for the counterflow heat exchanger. This is delta T1 for the parallel flow, and that is delta T2, right? So from here you can get the log mean temperature difference. And as I told you before that, Q heat exchanger is equal to Q hot is equal to Q cold. And Q hot is basically m dot hot Cp hot delta T hot. And Q cold is m dot cold Cp cold delta T cold, right? So if you have the temperature difference of any stream, you can get the outlet temperature of the other stream, or the inlet temperature if it's not given to you. So this is basically what we have here for the double pipe heat exchanger. And also Q is going to be equal to U, the overall heat transfer coefficient, multiplied by the area multiplied by delta T log mean temperature difference. So if you remember that U is the overall heat transfer coefficient, and it is equal to 1 over R total, which is the summation of the resistances. So basically this is the overall heat transfer coefficient. Area, the total area of the heat exchanger. Sometimes the question gonna ask you about what will be the total area of the heat transfer coefficient, the total area of the heat exchanger. So when you get the Q from here, and you have the overall heat transfer coefficient from 1 over the summation of the resistances, and delta T log mean temperature difference from this equation. So you can get the area of the heat exchanger. So this is for the first type of heat exchanger, which is the double pipe heat exchanger. We have the second type. I just wanna tell you all types of heat exchanger. You have to look at them from the lecture. You have to study them from the lecture. The cross flow heat exchanger. So the cross flow, this is the second type, all right? So the cross flow heat exchanger is either finned. It has also two categories, or unfinned, where we have like a set or arrays of pipes. We have like sets of, if we have like, I'm gonna draw the finned one, right? So you're gonna find the schematic of the other one in the lecture. So we have a pipe, array of a pipe. This way is the array, and the pipe, and it is finned. Finned is this way, and the flow is coming. This is the flow direction. While the other flow direction is going to come from this side. So we call it cross flow heat. So this is the cross flow direction. All right, this is the second type. The third type is a shell and the tube. The third type of the heat exchanger is shell and the tube heat exchanger. So the shell and tube is basically if we have a very big shell heat exchanger where
Sorry, Sherry, can you go back up to the fin drawing for the cross flow heat exchanger?
This one? Yeah.
Yeah.
Yes, here. So this is the cross flow. You're gonna find the drawing in the lecture, and you're gonna find the drawing for that one as well in the lecture.
Okay, I'm finished. Thank you.
All right. So I'm just trying to tell you the major types of heat exchangers, and everyone has different categories, right? So from this is the shell and tube one. So if we have the tube coming, the inlet's coming this way and the outlet is this way. So this is the tube inlet, and that is the tube outlet. So the tube inlet is and outlet is this, and basically, sorry, and basically so this is the shell entrance. So the flow is going to go this way on this path and gonna leave from here. So this is the shell outlet. So this is the Shell&Tube. Sometimes it has one pass, sometimes it has two passes, and based on the number of passes and number of tubes, you're gonna find the different um, um, number of transfer units or different correlation that you're gonna get the effectiveness of the heat exchanger and number of transfer unit of the heat exchanger as well. So I'm gonna write this note here based on the number of passes and tubes, um, the effectiveness will change. I'm gonna define the effectiveness um, just in a minute. So the first type, which is the last type that we have, the first type is the compact heat exchanger. But I'm not going to talk about it. Compact heat exchanger. I just leave it to you to read about it in the lecture. Compact heat exchanger. So compact heat exchanger is something like the major application for that is the PC processors. You're gonna find it. This kind of heat exchanger is the processor for the any computer or any PC. So I told you about the heat transfer, the overall heat transfer coefficient. So again, for the overall heat transfer coefficient, 1 over UA is going to be 1 over U cold A cold is going to be 1 over U hot A hot, and this is going to be the summation is equal to the summation of the resistances, which is 1 over HA from the cold side plus 1 over sorry, um, this is the wall, our wall, if we have a thickness. So this R wall is due to conduction, and this is 1 over HA hot. So this is from the cold stream, and that one, and this is the heat transfer of the cold stream by convection, and this is conduction. And that one is convection from the hot stream. Sometimes if the thickness of the tube is not given to you, so if the thickness not given to you, is not given, then RW can be neglected. So RW is equal to 0. Right? So that's so far what I just want to tell you about this. So the last thing I want to tell you about it is the effectiveness. Heat exchanger effectiveness is, we call it epsilon, this way or this way, is the gain over the maximum gain, or the gain we see if the main function of the heat exchanger is to cool something or is to heat something, right? So it's going to be stated to you in the problem. So he's going to say that this heat exchanger is going to be heat a certain fluid or to cool a certain fluid. So this is going to be the gain The maximum gain, the maximum possible gain I can get from the heat exchanger not possible, which is ideal. So this effectiveness has a specific Q over Q maximum, Q gain over Q maximum. We call it Q, and the Q maximum is capital C. I'm gonna tell you what's capital C. T hot in minus T cold in. All right. So this capital C is basically m dot Cp. All right. Um, we call it specific heat rate. So this is the specific heat rate. All right. So the C minimum is either two cases, is maybe m dot hot Cp hot and m dot cold Cp cold. So you got to calculate the value of that one and to calculate the value of that one and see which one is the minimum and substitute it here. And another dimensionless number that we really take care about in the heat exchanger is NTU, number of transfer unit. Number of transfer unit, which is U, the overall heat transfer coefficient, multiplied by the area of the heat exchanger over C minimum as well. So the C minimum, as I told you before, is either m dot hot or m dot cold Cv cold, right? So I don't think the number of transfer units is gonna be given to you in the problem, but it might be asked from you, and from that number of transfer unit, you can get the total area of the heat exchanger. So far, this is the summary of the lecture. It's not the total summary of the lecture, but this is the maximum I can do right now. And if you have any questions, just let me know. I will start the solving two problems, each in 15 minutes until we finish the tutorial. Right. So the first problem. Does anyone have any question up till now so far? Does anyone have any question? All right. So question number one. Oh, sorry, that's question number two in the tutorial. I'm gonna upload the tutorial solution for you after, and I'm gonna upload these notes as well. I'm recording the meeting and be posting it. I will post the link so for the students who didn't attend the online tutorial, they can find it somewhere. So for question number two, is a counterflow heat exchanger. So guys, because I think the tablet is gonna finish. It's gonna. All right, so we have 15 now. We have 15 right now. Oh, so counterflow heat exchanger, we have two concentric tubes, as I told you, double pipe counterflow heat exchanger. So this is basically the very simple schematic of the heat exchanger, and where the cold stream is going in the middle. cold stream is flowing in the middle within a pipe diameter of 25 millimeter, and the hot stream is a counterflow. So this is the hot stream going to the opposite direction, where the diameter is 45 millimeters. So take care about the heat exchanger problem, because this is one of the longest problems in the heat transfer course. So take care, be wise, using the time during the exam. So the hot stream is basically oil, and this is gonna be the TX diagram. I think you have to draw the TX diagram in while solving the problem in exam. So it's gonna make it easy for you. So this is T hot in, which is around 100 degrees Celsius, and T hot out is 60 degrees Celsius, while the cold stream is entering at T cold in 30 degrees Celsius, and he told you that the T cold out is 35, T cold out is 35 degrees Celsius, and so given to you, m dot cold stream is 0.2 kilogram per second, and for the hot stream, m dot hot is 0.1 kilogram per second. So the question asked for is what is the tube length? So what is the tube length? And he told you that to assume that T cold out is 35 and justify it. So I tell you how to get this, and I tell you how to justify that thing. So what's going to be the tube length? As I told you, for the double pipe heat exchanger, Q is going to be U A delta T log mean temperature difference, right? So we don't know U. The area is going to be pi the inner multiplied by the length. From here, we're going to get the length. Delta T log mean temperature reference, we don't know it, but we can calculate it. Q, we know Q because we have one of the streams. We have all the properties of the stream. We have m dot, we have CB, we can get CB, and we have the delta T of the hot stream. So first of all, we'll be solving this is this way. So Q is equal to Q hot is equal to Q cold. And if you have any questions, just let me know. So Q hot is m dot hot CV hot delta T hot, which is equal to m dot cold CP cold delta T cold. CP is not given to you. So what we're gonna do is I'm gonna write it on the right side here. So for the hot stream, the average temperature of the hot stream is T hot in plus is the average temperature of the inlet and the outlet. T hot out over 2, which is 100 plus 60 over 2, which is 80 degrees Celsius. So at this temperature, for the hot stream, which is oil, okay, so the hot stream is oil. From the table, you're gonna get you will be getting CB of the hot stream. This is going to be 2131 joule per kilogram Kelvin. And also you're going to get mu. We're going to use it later to get the heat transfer coefficient the, by force of convection for the hot stream, and I'm going to do the same to get the heat transfer coefficient for the cold stream, and from both of them we're going to get the overall heat transfer coefficient, this one. So all right, so let's start by doing this. Mu hot is going to be 3.25 multiplied by 10 to the negative 2. K is 0.138. And for the cold stream, the average temperature is going to be 35 as given to you, plus 30 over 2, which is going to be 32.5 degree Celsius. So from here, I'm going to get Cp is equal to 4178. This is for water, right? So the cold stream is water. And Cp is cold is this thing, joule per kilogram Kelvin. Mu is 725 multiplied by 10 to the negative 6. K is going to be 0.625. All right, so let's get back here.
Sharif, the
Yes,
35 is the assumed CL, right? TCL, right?
easy out. Yeah, the cold temperature, the outlet cold temperature.
Okay. All right.
Yeah, yeah. So let's get back here. Q, we can get Q from here. M dot hot was 0.1. Cp hot, this one is going to be 2131 multiplied by delta T hot, which is 100 minus 60. So this is going to give you 8524 watts. And this 8524 watts, 8524 watts is going to be equal to the cold stream as well. So let's write this here. So the cold stream is 0.2 and Cv cold is 4178. Delta T cold is T cold out that we don't know. We just use the cold out, the temperature that is given to you. Actually, where are we getting 35 from? Yeah, this 35 is assumed. 35 is assumed. So in the problem, he told you to use that 35 degrees Celsius as an initial guess, as an initial assumption, and he asked you to justify it. He gives you that initial assumption to allow you to get the properties. So we used initial assumption to get the properties. That's why he asked you, yeah, thank you. That's why he asked you to justify it, right? So T called out minus T called in, which is 30. So T called out, when we get T called out from here, was 40.2 degrees Celsius. So, which is very close to T called out um, um, assumed, which is 35 degrees Celsius. Assumed. So therefore we can proceed. So now T called out is justified because the difference is not too big. So we're gonna go ahead with this one, with the new one, this one, right? So turning back to this equation, we call it equation double star, right? So this equation we have Q. Right now we have Q. Let's go get delta T log mean temperature difference. So to get delta T log mean temperature difference is delta T1 minus delta T2 over len delta T1 over delta T2. And if we draw the TX diagram again, very quick, 100, 60, 30, and 40. All right, so basically this is delta T1 and that is delta T2. So returning back here, so delta T log mean temperature difference is going to be 100 minus 40 is 60. Delta T2 is 60 is 30 over len 60 over 30. This is going to give you a log mean temperature difference equal to where is it? Yeah, it's going to be 43.2 degrees Celsius, right? So now we have delta Tm, delta T log mean. Then what about U? So let's go get U right now. So to get U, the overall heat transfer, as I told you in the beginning of the lecture of the tutorial, is U1 over R total, which is 1 over the summation of the resistances. Okay, so U is equal to 1 over HI plus R wall plus 1 over H out. Okay, so thickness not given, so we can neglect this one. RW is equal to 0 because the thickness of the pipe is not given. So we're gonna left with 1 over HI plus 1 over H out. And the dilemma here is to get HI and H out. So both of them are force of convection. HI is a flow inside a pipe. H out is flow inside an annular pipe. So both of them has different Nusselt number correlation. So let's start with the HN. I will be doing it this way. Okay. So HN, how are we gonna get HN? So basically this is forced convection droplet. We get Reynolds number when we have a mass flow rate. So Reynolds number is when we have a mass flow rate. So Reynolds number is 4 m dot over by the mu. This is the n, obviously. So 4 m dot of the cold stream was 0.2. I remember kilogram per second. Pi dn, which is 25 millimeters, 0.025, multiplied by the mu. We get it at the average temperature of the cold stream. What was mu? Yeah. So mu was 725 multiplied by 10 to the negative 6. So Reynolds number in that case 14,050, which is higher than 2300, the critical Reynolds number for inside flow, for flow inside a pipe. So basically it's a turbulent, and we're going to use this Nusselt number correlation. Nusselt number is going to be 0.023. Reynolds number 4/5, Prandtl number is 0.4, and um, we have Reynolds number, Prandtl number. I didn't tell you Prandtl number. Oh, I didn't tell you Prandtl number. Prandtl number you're gonna find it in a solution, but I don't remember. Yeah, so here you're gonna get also Prandtl number. Don't forget. Okay. So we get Nusselt number 0.90, and it's gonna equal to hi di over k. Hi di was 0.025 millimeter. It's gonna be in meters over k, which is 0.625. So hi is 2250 watt per meter square Kelvin. That's hi. Let's get back to h out. So this is a forced convection. Forced convection. Annular pipe, right? So Reynolds number for annular pipe, Reynolds number is going to be 4 m dot over pi d out plus d in mu. So when we substitute these values, it's going to be 4.1 over pi d outer is 0.045 plus d inner is 0.02 multiplied by the mu. And the mu of the oil was 3.25 10 to the negative 3.25 multiplied by 10 to the negative 2. So Reynolds number here is going to be 56, which is very, very low. And in that case, this is going to be laminar plus annular flow. This is going to give you a Nusselt number. From the table, you're going to get this Nusselt number from the table in the faucet convection lecture. Nusselt number here is constant, which is 5.63. So Nusselt number in case of annular flow is going to be h out hydraulic diameter over k. So the hydraulic diameter here is going to be d out minus dn. The hydraulic diameter for any. Sorry, I didn't get the message. Oh, I have 4 messages. Could you please explain again why we are adding the 2 diameters? Okay, so it's gonna take long. Okay, look, I'm gonna do it right now. All right. Over. Okay. So you're talking about this one. You're talking about this. I will show it to you right now. So, right?
Yes.
All right. All right. I'm gonna come back. I will get back to you right now. So, for this thing specifically, all right. Reynolds number is rho. You mean d over mu, and this is the hydraulic diameter, right? So I wanna make it in terms of mass. I wanna make it in terms of mass. So mass m dot is equal to rho u mean multiplied by the area. All right, and so we can substitute rho u mean by here, put it here. So Reynolds number is going to be m dot over m dot d hydraulic multiplied by the area multiplied by mu. So we have m dot here. Hydraulic diameter is known to be d out minus d in. All right, and the area of this the area of the annulus area is basically pi over 4 the outer square minus the inner square, and this also is the outer, so we can refine this bracket into the outer minus the inner multiplied by the outer plus the inner. So if you substitute that here, you're gonna find that Reynolds number is going to be m dot the outer minus the inner over pi over 4 the outer minus the inner multiplied by the outer plus the inner multiplied by mu. So if you cancel that with that one and get these 4 out up there, you're gonna find that Reynolds number is going to be 4 m dot over pi d out plus dn multiplied by mu. That's why. So you're welcome. So let's get back here. I don't think I'm gonna make it for make another question, but that one was very, very long. So let's get back here. So H out from that formula is going to be or H out the hydraulic over K is Nusselt number, which is 5.63 or 6.5. This is going to be H out multiplied by 0.045 minus 0.02 over K, which is 0.13. So basically H out is going to be 38.8 watt per meter square Kelvin. And from both of those, from H in and H out, we can get U is 1 over H in plus 1 over H out. It's going to be 1 over H in is 1 over H in was 2250. Sorry, again, what was the question? Where did you get 0.02? This is the inner diameter.
Yeah, but isn't the inner diameter 25? Didn't you say it's 25?
Yeah, sorry, 25. That's right. Thank you. Plus 1 over 38.8. This is gonna give you your overall heat transfer coefficient 30. Oh my god, is 38.1 watt per meter squared Kelvin, and so we get Q. So substitute all into equation double star, which is Q is equal to U A delta T log mean temperature difference. So basically, the Q we get the Q was 8,524. U we just get it right now 38.1. The area is pi di multiplied by the length delta T log mean temperature difference is 43.2. So the diameter, the inner diameter is 0.025. So we left with the length. So the length of this of that heat exchanger was 65.9 meters, which is very, very long.